section 3.6 special matrices. Yeah, you will see some extra information from this website, web addresses. In this section, we will see various properties of matrix. In the earlier sections, we discovered various properties of matrix operations. Now, we introduce several special matrices and consider some of their crucial properties. First, diagonal matrix. It is a square matrix with entries except the main diagonal entries are all zero, like this. The diagonal matrix is a square matrix whose off diagonal entries are all zero. So this matrix can be written as this, just diagonal of these, which are that each of AII's represented the entries in the main diagonal. So when you write this, this means this type of matrix. Identity matrix is a special case of a diagonal matrix whose main diagonal entries are all 1. So we write the identity matrix as IN like this. This is n by n diagonal matrix. We write. And scalar matrix is just a scalar multiple of the identity matrix. These all three are the examples of a diagonal matrices. Scalar matrix has a nice property as well. The following are all these are all diagonal matrices. This is identity matrix and this is a scalar matrix. Okay? So when we define a diagonal matrix like this, then this means this is 2 by 2 diagonal matrix whose main diagonal entries are 2 and minus 1. And this is a 3 by 3 diagonal matrix whose main diagonal entries are minus 3, 2, and 1. So if you type it, then you will see like this. Yeah. So you will see. If you want to have a 4 by 4 matrix like this, then you will have a 4 by 4 diagonal matrix like this. Consider the following matrix, DA and DA. If you multiply this diagonal matrix from the left on the matrix A, then the result matrix is like this. What this means is when you multiply a diagonal matrix on the left, then its work is just a scalar multiple of DII to the ith row of the matrix. So this, as you see, the DA is just 1 times the first row and minus 3 times the second row of A and 2 times the third row of A are representing for the matrix, each rows of DA. So when you multiply a diagonal matrix, then you can easily expect what the output looks like. And also, the diagonal matrix has a nice properties like this. The inverse of a diagonal matrix is just another diagonal matrix whose main diagonals are entries are reciprocal of the identity matrix of the original one. So just inverse of the main diagonal entries. Because if you multiply these two, you will see automatically this is going to be an identity matrix. And the power of the matrix, diagonal matrix, is just the power of the main diagonal entries. And the inverse of this is just the inverse of the main diagonal entries are there, the diagonal matrix. And you can easily check if you have a diagonal matrix D like this, D inverse is just reciprocal of the main diagonal entries of D is like this, and fifth power is like this. If you want to have one, it's 25th power, then 25th power would be like this. So this is just the diagonal matrix whose main diagonal entries are the 25th power of the diagonal entries of the original matrix, original diagonal matrix. Okay. And here, if A transpose is equal to A, then we call this matrix A is symmetric. If A transpose is itself, then it is called a symmetric matrix. And if A transpose is equal to minus A, then we call A is a skew symmetric matrix. Symmetric matrix and skew symmetric matrix. Okay, so in this case, as you see, 2 and 2, 3, 3, 6, 6. So the shape of this matrix is symmetric. So this is a symmetric matrix. Here, 1 and minus 1, and minus 2 turns to be 2, 3 turns to be minus 1. So this is a skew symmetric matrix. And this identity matrix is an example which is a symmetric matrix, but not skew symmetric. And you suppose we can check it. If we define a matrix A and B like this, then you will see A and A transpose is the same, so it's true. And B and minus B and B transpose are same, like this, true. So from here we can check A is a symmetric matrix and B is a skew symmetric matrix. If you check in this way, then you will see B is not a symmetric matrix. Important fact is this. If A is any square matrix, then A plus A transpose is a symmetric matrix, and A minus A transpose is always a skew symmetric matrix. Because the transpose of A plus A transpose can be written in this way, which is same as the original one. So A plus A transpose is a symmetric matrix. But transpose of A minus A transpose can be written in this way. So this is a minus times minus A times A minus A transpose. So so A minus A transpose is a skew symmetric matrix. Important fact is every given matrix is an addition of these two matrices. The first part is a skew symmetric matrix, and the second part is a skew symmetric. So every matrix can be written as a summation of a symmetric matrix and skew symmetric matrix. If you have any matrix, then you can split it as a symmetric part and skew symmetric part, like this. And a square matrix whose entries under the main diagonals are all 0, then we write this upper triangular matrix. Square matrix whose entries below the main above the main diagonals are all 0, then we call it a lower triangular matrix. Okay. Yes, and properties of a triangular matrix. If A and B are lower triangular matrix, then product of those two matrices are lower triangular matrix. And if A is an invertible matrix, invertible lower triangular matrix, then A inverse is also a lower triangular matrix. If ai is equal to 1 for all I, then the main diagonal entries of A inverse is also all I ones. These are the properties of the lower triangular matrix. This is very important. You may check what? The first part. 그 6쪽. 자네 이름이 뭐더라? 김강석군. CRM 3.6.1의 파트 1. 요거 내가 해놓은 거 웹에 찾으면 있어요. 한번 찾아서 올려놓도록 하세요. Product of two lower triangular matrices is a lower triangular matrix. Why don't you try to share the proof of this first part of it? Okay, next. If let A be a square matrix, if there exists a positive integer k such that A k's power of A is equal to a zero matrix, then A minus A, I minus A is invertible matrix, and the inverse of A minus A is equal to this. How we can prove this? How we can show this? all you have to do is just multiply this I minus A and this matrix to show it is an identity matrix. And this means the inverse of this matrix is this, and inverse of this matrix is this. This is true because A to the kth power is equal to 0. So all the extra terms are going to be a 0. So you will see this, the product of this matrix is equal to 0. Mr. Park Jong-woo, why don't you check this and share it, okay? And the others are the exercises. Here is the movie clips that the student, my former student, explained the solutions of the each sections. So you will see, you will check. And also there is a solution in here. So you will find all those you will find I have uploaded the solutions, but here is the solution already. So here you will see true false problems and the computational problems. So you now have the problems for chapter 3 here, and you can go through, and some of the team 1 will give a presentation of the solution of the problems in chapter 3. I think that's the end of chapter 3. Okay. Here, also. Okay. I think that's it. Any questions on section 3.7, special matrices, and other questions in chapter 3?